Hey everyone, welcome back to Robotics. I hope you guys are doing well. Today we have our 30th lecture on gradient descent. Okay, so let's get started with a video. Now, this is a video of reinforcement learning. All of these agents are playing hide and seek. The players in blue are trying to hide, and the agents in red are trying to find them. At the beginning, the players move around pretty randomly, and that's because they don't have a very good control policy. But what they're going to try to do is to learn a control policy over time through experience. They're going to test things out, see what works and what doesn't work, and then use that feedback in order to improve their controller and eventually get pretty good at this game. So overall, I like this video as an example of reinforcement learning, of learning from experiences in order to improve my robot's behavior. And that's what we're going to be talking about in today's lecture. First, I want to show you some of the differences between supervised learning and reinforcement learning, and then I want to kind of go through a simplified reinforcement learning problem where we can apply gradient descent in order to tune control gains. Okay, so I want to begin with set the stage by recapping control policies. So here's my control policy pi, and this control policy, it's going to be a mapping from states to actions. Importantly, this control policy is parameterized by weights W. And I don't really know the right weights to have, but I want to make sure the robot learns those weights in order to complete its task that it's given. So whatever that task is, learn the weights in order to maximize your performance or minimize your loss function. But where am I going to get the data that I need in order to train these parameters? Like surely I need some sort of idea of states and actions and outcomes in order to figure out the right control policy to have. Well, there's two main ways that robots can get this data. The first one is supervised learning. And the idea here is there's going to be an expert, maybe it's a human, that's going to show me examples. They're going to say, okay, if you're at this state X, this is the action U that you should take. Again, they're giving me examples of the correct behavior. We've actually been working through this in some of our previous lectures when we talked about linear regression. You might remember that we collected this expert data set where at all these different states X, the expert told us, okay, these are the actions U that you should take. This is an example of supervised learning or learning from examples. I want you to contrast that with reinforcement learning. Instead of providing labeled data, what if we let the robot learn by repeatedly interacting with its environment? Take this example where the robot is trying to reach inside this box. Maybe the first time it fails, but sure, it collects some more state action pairs and it understands what didn't work. As it keeps collecting more data, and again, building out that data set of things that worked and didn't work, eventually it can learn a policy that successfully reaches inside the box. So again, we're collecting data through experiences either in simulation or the real world, and I'm using that data and the successes and failures within that data to update my control policy. So I want to draw just one final contrast between these two very different approaches. Again, with supervised learning, I am learning from examples. The robot is given some data set of expert behavior, and these examples include inputs and outputs that are labeled, saying at this state X, these are the actions that you should take. Maybe think of an analogy like autonomous driving. Maybe I can teach a car how to drive by showing examples of how humans drive. That would be an example of supervised learning. Now, on the other end, reinforcement learning is learning from experience. The robot is given a loss function, and then it's going to interact with its environment, either in simulation or the real world, in order to find behaviors that minimize that loss. If we stick with the autonomous car, it could be that I tell the car, hey, here are all the rules of the road, like you have to follow these rules, and here's something you should optimize for. Now try it out yourself. And in sim or reality, the robot might build up a control policy that does well at this driving task. Okay, so that's the theory, but what does the practice look like? How can I actually train robots using experiences in order to learn these weights W? Well, today I want to work through one example, and this example is grounded in what we've talked about before for dynamics and control. So it kind of connects some of our previous topics. So what we're going to have is we're going to have a robot that has a very accurate model of its dynamics. And it's going to use this model to test how different control gains affect its performance. Specifically, I'm going to look at multivariate control. So here's my multivariate control law. And I want to tune my proportional gain matrix. I'm going to assume that everything else remains fixed. And I just want to figure out what's the best proportional gain matrix to make my robot move to its desired position. And within this matrix, I'm going to be looking at the diagonal terms for W1 and W2. So these are the two weights I'm going to try to tune using reinforcement learning. My goal is to learn those weights so that the robot quickly and accurately moves to its desired position. So I'm going to start off at some theta, and I want to very quickly move to theta d. So my error is just going to be the cumulative loss between these two, between my actual and desired positions. And this goes back to the basics of control, right? Because we said that in control, our goal is to try to drive my system very quickly to its desired position. In the past, we tuned our control gains kind of in an ad hoc manner, just trying and seeing what works. And maybe that's a reasonable starting point for this problem as well. So I want to explain this. I'm going to start off with the video, and then I'll talk a little bit about the overall idea. So in this video, I've got a Revolute robot arm. Here's my first Revolute joint. Here's my second Revolute joint. And then here's my end effector. This robot is moving in a plane where gravity is pulling it down, and I've got a very accurate model of its dynamics. So I can simulate this robot and see what happens. Now, I've chosen some initial control gains, and these are making the robot move towards its desired position. So I've started off with, okay, I think these gains could be reasonable, and now I'm simulating the robot. I'm seeing that they're okay, but not great. I've measured my loss. Again, this is the cumulative error between my desired position and my actual position. So maybe a naive next step would be, let's just try tuning the gains, right? As a user, I can just try out different gains. Maybe I pick 100. Okay, it's a little bit better. I've got a little lower loss. Crank that up again. Maybe I've got 1,000. Again, my loss gets slightly lower. But as you can see, this doesn't really scale well, because that would mean that I, as a user, I have to try all these things myself and see, okay, maybe this works, maybe this doesn't. I'm going through the whole trial and error myself. I want the robot to do this trial and error itself and learn from its own experiences. And so that's going to lead us towards our algorithm that we're going to use for this reinforcement learning approach. And what we're going to use is a little bit of a better solution is we're going to take advantage of gradient descent in order to tune W by itself and minimize the loss. So here's the general pipeline for how we can apply this gradient descent to our reinforcement learning setting. So I'm going to initialize my weights with whatever my first guess is, and I could pick just whatever I like, some weights for my proportional gain matrix. Maybe I start off with ones along the diagonal. Sure. So I've got my initial guess of my weight matrix. And then I'm going to go through this for loop. And at every step of this for loop, I'm going to update my understanding of what I think the weight should be. And then finally, I'm going to return my best guess of, okay, I think these weights are going to lead to the best performance. I want to go through these steps in a little bit more detail. The first step is I'm going to simulate my robot. I'm going to say, okay, if I have these different gains for my proportional gain matrix, how do things play out? So I'll simulate my robot and see how it behaves. And I can only do this because I've got this accurate dynamic model and I understand how my robot moves in the simulation. Then, based on that simulation, I can extract a numerical estimate. This is an estimate of the gradient that says, okay, if you were to change the weights, this is how my loss function might change in response. And then I can plug that into my gradient descent, my update rule, and I can use that to update my value for W. So the intuition I want you to have here is I've got an algorithm that can simulate the robot arm with multiple different values of W, and it can choose the next value of W intelligently so that I decrease my loss function. So again, the robot is by itself, autonomously trying to update its weights through experiences, seeing what works and what doesn't, in order to find the weights that are going to have the best control performance. And here I'm visualizing that process. I want to start off with the text on the left. So I've got my initial value. I just start off with ones on the diagonal. And I set a lower bound. I said, hey, I know that in order for this thing to work, you can try different values of weights. That's totally fine. But never try values for weights that are below 0. And I know that I can't do that because it would cause my whole thing to become unstable. Similarly, I've got some upper bounds. I said, sure, you can increase the weights as you see fit, but don't go beyond 2,000. And my thinking here was, okay, there's got to be some upper bound beyond which my robot can't move that fast, or I'm demanding too much from my motors. And I just set it as 2,000 for this example. And then finally, I'm doing my optimization in this last step. Now, under the hood of this optimizer, I'm using gradient descent in order to update my weights in order to try to minimize my loss function. The optimizer is taking advantage of my simulations, testing and simulating different values and seeing what works and what doesn't, and using that to find the best value for my weights W. And over here, this is one of the answers that you can get with this approach. For this specific desired position, the robot figures out that actually I don't need to do anything for the first joint. I just need to tune my gain for my second joint for my robot to quickly reach that desired position, and it's got lower loss than what we had before. If you want to try this out for yourself, I encourage you to do so. Just download the practice set and the code that comes with it, and you can test this out, do your own reinforcement learning approach, and see what works and what doesn't work. Like I mentioned in previous lectures, for this practice set, it'll be in the description or the pinned comment. The first page has the questions, and the following pages have their solutions. Overall, in today's lecture, we talked about some of the differences between supervised learning and reinforcement learning. And then we also applied reinforcement learning for a kind of a model-based simple example where we were looking at gradient descent to tune some control gains. This lecture is going to wrap up all the different modules on learning, and now I want to switch gears and start thinking about motion planning. So we'll pick that up in our next lecture.